My name is Dave Krall. This is the continuing episode of our Masterclass series. The concept behind this is that we invite experienced simulation professionals to talk about any simulation-related topic that they're interested in. So if you feel you have something to offer, please contact me. We're always interested in having more people talking in this series. We have had in the past people such as Robin Clark, who we have today, Averill Law, Tom Schreiber, Al Pugh, all well-known people in the simulation community. So to introduce Robin, Robin Clark is an instructor, model builder, Mod L, block scripter, and partner in the QMT Group. For the last 7 years, he has trained hundreds of beginner and advanced simulation students. I think many of you have taken his classes here. He's designed custom blocks and built numerous simulation models for his customers. I work with Robin quite a bit in training and at conferences. He's always a pleasure to work with and has excellent technical expertise.
Okay, I'm ready to begin. Thanks for the introduction, Dave. Before I begin, I would like to say a couple of special thanks out there for the people who have helped me put some of this stuff together. Number one is Dr. Botkin from the University of Tennessee, who has helped me with the supply chain model that I built, and also Cecile from Imagine That, who gave me the example for the LP solver example that I picked apart quite a bit of it in putting together some of the blocks that I did here. Thanks, guys. A little bit more about myself. Yes, I have been doing modeling, training, coaching for about 10 years. Before I did that, I worked a little bit in optimization, building software for people to use in the blending industry, like making hot dogs and hamburgers, trying to put the lowest cost meat together that still meets specifications. So that's my optimization background. Here's what we'll do today. In order to look at how optimization can be used in a simulation model, the best way to do it is through an example. So we'll spend about 20 minutes looking at the supply chain model that I built. It's just a basic discrete event supply chain model. We'll look at the ins and outs of it, and then we'll spend about 20 minutes on the mixed integer programming model that I've incorporated into the simulation model. And then in the last 20 minutes, we'll spend looking a little bit at the evolutionary optimization in ExtendSim, the block that's found in the value library. So that's how we'll divide our time up, about a third to each of the topics. After each of the topics, I'll give you guys some time to explore questions on the particular topic that I'm on. But we will start with the supply chain model first. Now, this could have been applied to any number of topics, but one of the common optimization models out there that people use to solve in industry is a transportation model. So I thought, what better way to illustrate optimization in a simulation model than building a supply chain model which looks at those same issues. So here's my supply chain model. Well, this is a screenshot of it, where I'm looking at a series of distribution centers or warehouses. Those will be in the black dots. You'll see them at Portland, San Diego, Houston, Tampa, DC, and Chicago. And a few plants that are supplying those distribution centers. Those would be the red dots or the orange dots at LA, at the ATL, and New York. And you know, one of the questions for this type of model is, well, are we really supplying the correct plants from the correct distribution center? Or do we need all these plants? Could we deal with fewer plants? Things like that, those sort of issues. So in a nutshell, that's the type of model that we'll be looking at. And as I mentioned, the two questions that I have is, do we need 3 plants? And once we determine if we do need 3 plants, the next follow-up question will be how much safety stock should be kept on hand at those plants or at the warehouses. Safety stock is an important issue. But if I go down to 2 plants in this type of model, the first question is, which 2 plants should be kept? And the follow-up question would be, how much safety stock should be held at those 2 plants and the following distribution centers? But the question of how much safety stock is needed, that can't be answered until the first question is answered. Should I have 2 plants or 3 plants? And if I have 2, then which 2? Because the amount of safety stock that is needed at the locations is entirely dependent upon the network. In actuality, with all of this, it means that there's going to be a lot of combinations that we would need to test. If we were just doing a pure simulation model, that would be an astronomical number of scenarios that we would need to run through. So the use of optimization in here would be to reduce the number of scenarios that would be needed. So the optimization is here to help us eliminate some of the bad combinations up front, so that when we're doing the experimentation in the simulation model, we're more doing some fine-tuning, not doing a shotgun approach. As I mentioned, the approach is going to be in 3 stages. Number 1, the mixed integer programming model. And this is going to be based on 2 things. Number 1, the transportation cost. We want to make sure we're getting it from either the closest or the place that would have the cheapest transportation costs from us. That still would be under the plant capacity. Plant capacity is a very important issue here. So we got to make sure we meet that constraint. Then we would go into the evolutionary optimizer, and we would be looking at the order point at each of those locations, each of those location product combinations, to help us get us in the realm of where our safety stock needs to be. Then finally, we would use just a plain discrete event model to help validate the answers that we have based on randomness. Because if we're looking at the mixed integer programming model, it wouldn't really be based on randomness. It's just more of a deterministic problem, a deterministic model. So the use of simulation here is going to be saying, yeah, I know that if the demand is on average going to be 10 pallets a day or 10 pallets or 70 pallets a week, what happens whenever sometimes that's 40? Or what happens if that's 140 pallets? How does the supply chain react over those varying conditions? And that's something that we can't really take into account very easily in the mixed integer programming model. And here's how the pieces fit together. Again, I'm going to go over the overall structure of it, and then we'll delve into each individual piece. But at the core of it is the ExtendSim database. Because the ExtendSim has a really rich development environment with the database, that allows us to interact with the simulation model very easily to get the data into and out of the blocks as we need to. That also allows us to write code in the simulation model to interact with an optimization solver, a DLL, to help us formulate the problem and solve the same problem with the same data structure as we had in the simulation model. And then, again, since we have the ExtendSim database, we can also build into it the evolutionary optimizer to allow us to solve the safety stock problem. And the key of it is we're not going to different applications trying to import and export data, trying to get the data to match up in all these different applications. But because ExtendSim has this really rich data database backend, and because of the development environment, we can do a lot of these things in one single tool. And that makes it a lot easier to interact with the model. So first we'll dig into the discrete event portion. So we have a process flow here where we have raw materials upstream, we have the warehouses downstream, we have the plant in the middle. So with the process flow in the scope of it, we have warehouses at the downstream end, close to the customers. That's where consumption occurs. Consumption, and that's one of their assumptions, that consumption is only going to occur at the warehouse here. And in this case, we have 6 DCs or 6 warehouses. And sorry, I will say DC sometimes, and I will say warehouses sometimes, but I use that term interchangeably. They will place orders up to the plant level, and the plant will send them products. The plant, in return, is going to be supplying the materials to the warehouse, and when they get low, they'll place orders to raw materials upstream. The raw material, in response, will supply products downstream to the plant, and there is an infinite supply of raw materials upstream. But it does take a little bit of time for it to go from the raw material area to the plant area. And this is what the network looks like. We have one raw material source, and that's generic, which is supplying the 3 plants. You'll see that labeled as node 2, 3, and 4. And then we have a question of which plants should supply which warehouses. And the warehouses are nodes 5 through 10. That question mark is the question that we're trying to answer with the mixed integer programming model. So again, some of the assumptions, I've already covered the first 2. Then we have plants do not ship to other plants, or warehouses do not ship to other warehouses. That's just an assumption that we make just to make it simpler to do the modeling. Could be modeled, but we didn't. But the reason a warehouse might ship to another warehouse is, well, instead of having the plant go make some more, if we just shipped it to the wrong warehouse, maybe we do a cross shipment. But we're not going to study that here in this problem. Unmet consumption is considered as lost sales. So if the customer at the downstream side next to the warehouses cannot get their material, then what they don't get would be considered lost sales. But we do send them partial shipments. Unmet demand internal to the supply chain is considered as back orders and will be shipped when available. So, so I know it's demand both internally and externally, but I'll make the distinction here that consumption goes on at the warehouse. That's what the consumer is consuming out of the system. But demand is internal. Demand is not customer-driven here. That's from a warehouse to a plant or plant to raw materials. I will say one other assumption is that demand here is random, but not seasonal. Now, it's easy enough to incorporate seasonality into the warehouse model or into the warehouse consumption in the simulation model as well as the optimization. But I wanted to keep it simple, and if it was seasonal, I would tend to make that a different model. So I would solve the steady state situation here, such as the way it is in wintertime, and another discrete event simulation set up to solve the problem when it is summertime. I would do that in separate models to see how the network would change between one season versus another. Just to keep it simple. The costs that are involved will be the transportation cost, the inventory holding cost, and the lost sales. This is where we cannot supply the customer consumption amount. There is not a cost for internal to the supply chain when the plant can't meet the warehouse's demand. I do not have a cost in there for that. That's just somewhat internal to the supply chain. But I do have a penalty there for if we can't meet the customer demand. Let's jump into the model here. There's a handful of important tables that I want to show you. So here's my simulation model. It looks like the PowerPoint that I showed earlier. Basically a map of the U.S. that I have here, and I have nodes up here. These nodes would, which most of you guys would be familiar with ExtendSim, but the nodes would represent actual locations. At each of those locations, we have areas where they receive orders and areas where they receive product and how to deal with them. That's what all the nodes look like. This is an H block in which all of the H blocks in here are very similar, except that I have changed the location ID from one node to another. But the important portion is the database. Let me open up and let's look at a few database tables here. The first set of tables is to be able to switch manually which locations I want to include or not include. So there is an option in here if I want to test to see Well, maybe I know I don't want to have a plant there at Houston. I can turn that on or off. Or maybe I don't want the plant at New York. I can simply flip a switch and turn that on or off. Also have a switch for the product. And in this case, I'm only modeling 3 products. This would be like a product family. Again, we could model every product, not an issue, but I tend to try to keep things more simple and focused. And the only real reason why I'd want to incorporate every product is if I want to look at issues around the size of the warehouses. And I'm not looking at warehouse capacity now, so that's not really an issue. Also have switches to turn on the locations, the location product combinations on and off. Some of the other tables in here would be plant data, such as the service time to take a raw material and turn it into a pallet of product, as well as the capacity, how many production lines are going on that product. Consumption table describes the amount of customer consumption that happens on, in this case, the frequency of consumption is on a 1 day, every day, and that's how many pallets are consumed out of the warehouse per day. Yes, this is all log normal based on a mean of 10 and a standard deviation of 4. So it's just an example model here, but just to illustrate the point, so I just left them all in the same distribution. And if we want to take a peek at what that distribution looks like, if I plot it, you'll see that the average is 10, and with a standard deviation of 4, it does go up to about 20 to a little over 20 pallets possibly a day. I have an inventory table, which describes things like the current amount of inventory that I have on hand based on the location and the product. You notice the raw materials product, the current amount is a really large number. Again, that simulates an infinite supply. I'm looking at the amount on order that's kept track of in the table, and the result of that would be the inventory position, which would be the amount on hand plus the amount on order gives us the amount, the inventory position. I'm also keeping track of the back orders. That would be an order internally in the supply chain that cannot be met, as well as lost orders. This would be an order from a customer that a warehouse couldn't meet. And also have here the initial amount that gets put into inventory at the beginning of each run. And the units here would be in pallets. I have another table for the inventory policies, things such as what the review period is. Should it be 1 day? Should it be a week? And what sort of policy am I looking at? Is it that I want to look at and review? When I do review based on this review period, I want to make sure that I'm below the order point. I'm going to have a fixed time of review. That would be the 1 day here. And I'm, the order quantity. That is, my order quantity is going to be fixed. So I have a fixed order quantity here. So when I do order, I place an order for 350 units. But I have a few other ordering policies in here, such as, when I do order, I'll order up to target amount. Another one is when I do order, I order up to the target amount, but only when I have reached my order point. So a few ordering policies there. Let's see here. That would be, I'm listing here my order point. Also listing the target if that is used. In this model, I'm not actually using the target amount with these inventory settings. I have the transportation data. I have a distance matrix in here that shows how far it is from any one location in the supply chain, from example, LA to New York, Atlanta, Portland, San Diego, to any other location. And I've numbered the locations 1 through 10 here, which relate to the record number. Raw materials would be 1, LA would be 2, New York would be 3, Atlanta would be 4, based on that numbering scheme. So the location 1 through location 10 matches up with the locations in this record order. So locations 2, 3, and 4 are the DCs, or the plants. Records 5 through 10 would be the distribution centers. When I run the model, so it's running for about, I believe, 100 or 120 days. And every day, again, the certain amount of material is being consumed here. You can see from the inventory table that the inventory is decreasing on a daily basis. And every so often we place an order, and you'll see the amount on order go up. On the top level, I'm not doing much animation. The only thing I'm animating is the customer fill rate. For example, if the San Diego is only getting, say, if it's getting 95% or above of its what it's requested, let's see here. If I look at the results, if I look at the amount of lost orders versus the amount supply or the amount ordered, if it had supplied, or if it had received 95% of its how much it ordered, you'll see it white. But as it receives less than what it has ordered, it turns yellow, then it turns orange, then it turns blue. So as we are not meeting our internal supply, we are the colors of the warehouses are going to be changing some. So that's the only thing that I'm animating on the top level, as well as the cost. I am animating the cost. But what you will see here as it's running, if I look at the order log, when the model is running, let me go in here and put a, let me pause the block, pause the model. I'll pause every 1 day. And as it's running, we want to take a look at the inventory and see how it's decreasing. You'll see the inventory decreasing. It looks like we might have reached the order point on some of them. So you'll be able to see an order log in here. So when I do reach the order point, I'm logging when I have ordered, the location, who the supplier is, and the product, and how much I've ordered. So I'm logging the orders, and then I am, when I do get to ship them, I have a shipment log of the supplier, the customer, and some of the information about that shipment when it gets supplied. You would be able to see the charts in here. If I open up the Portland, look at some of the charts here as I go from step to step. I have 3 plots here, one for product 1, 2, and 3. The blue line is the current amount of inventory. The red line is the amount on order. On hand, I'm sorry, it should be the amount on hand. No, current amount and the amount on order. Yeah, something like that. Or it could be the inventory position, I forgot. Nope, it has to be the inventory position. I have it mislabeled. But I am showing the inventory plots in here. When I do miss an order, again, I track that in the location products table for lost orders, or I track it under the back order amount. And I'm using that to figure out using that to look at the holding costs and the lost sales. I have a penalty for when I miss a customer sale. Also have a penalty for keeping inventory. And as a result, when the simulation is over, you will see at the end the holding costs and the lost sales appear in the cost structure here. Okay, as it's running, Let me go ahead and take a moment and see if there's any questions on the model itself before I dig into the optimization. Dave, are there any questions?
The only question I have is one that came in very early, which is, now I made an assumption that you were going to be talking using LP-Solve. Have you tried any other optimizers other than LP-Solve, or am I wrong? You're using something other than LP-Solve here.
Right now I'm using LP-Solve. The next iteration of this I'm going to be using Lindo. But right now it is LP-Solve.
Okay. So the mechanism for calling these is, as I understand it, fairly similar. They typically are set up as a DLL, and you call the DLL with certain parameters that you pass into the solver, and then it solves it and then returns the results back. You have to configure these differently, obviously, for the different solvers, but it's similar enough that it's not too difficult to swap one out for another one. So I don't see any other questions, Robin, so you can continue.
Okay. That is correct, Dave. It is fairly easy to switch them out. And in this section, I'll show some of the function calls that we can use to switch those out with. So here's my problem. I'm setting up a minimal cost network flow problem in here. So I have my nodes. Again, the plant, the plants would be 2, 3, and 4, where the warehouses would be 5 through 10, and the raw materials would be 1. And you'll notice this arc on here has a cost statement on it. So I'm tracking the cost as it goes from one node to another node. So here's my cost statement, and shows it going from 1 to 2 for product K. Again, I have 3 products in here, but that's my setup that I'll be using to look at the optimization problem. And again, the goal of this is minimize the transportation cost while considering plant capacity and customer consumption. The constraints that I have in here, I have a constraint for the consumption. We have to meet the customer demand. I have a constraint for the plant capacity. I have a conservation of flow constraint. And I want to make sure that the warehouses are sourced from a single plant. I have that constraint in here too. Here's what the formulation looks like, but let's not focus on that. That's too much equations for me. Let's look at the equations one by one in a simple example so we can see how I put it together. So in this case, I'll take a very simple example of looking at just one raw material node, 2 plant nodes, and 2 warehouses. So again, it's not the problem that I'm working on, but a simplification of it, just so we can see what the equations are doing. First of all is the objective function. Here's what the objective function looks like. If I take one of the terms here, the cost function that's going from 2 to 4, from node 2 to node 4, you'll see that with the red arrow. C24 is the cost of going from taking a unit of product, a pallet, from node 2 to 4. X is the amount that I'm shipping between node 2 and 4. So if the cost was 50 cents a pallet to go from 2 to 4, and the amount that I shipped was 10 units, X of 24 is 10 units, then the cost would be what, guys? It would be $5. It would be 50 cents. That would be the cost factor. The amount that I shipped, the X variable, would be 10 pallets. So the cost would be 50 cents times 10 pallets. That cost would be $5, just as an example. That's what each of those terms mean. If we look at some of these, the X terms, that would be the decision variable of the amount that is shipped from raw material to node 2. That's indicated by X12. X13 would be the amount of materials I'm shipping from node 1 to node 3. Then correspondingly, the amount that I'm shipping from 2 to 4 would be X24. Then the amount that I ship from 2 to 5 would be X25. That's where these terms come from. So every node in here, I have every transfer point I have in here, every arrow would have a cost function associated with it. And so I'm trying to minimize the total cost. And that's The next constraint, if we start looking at the constraint, will be the customer consumptions constraint. So assuming that in this case I have a demand of 10 at each of the warehouses, that would give me two equations in here. The first equation I would label X24 plus X34. The amount that's going from node 2 to node 4 plus node 3 to node 4, that must equal 10 units each time period. Because the demand is 10, the amount flowing into that node has got to add up to 10 units. So there's only two arrows adding into it, so I have two variables up the top feeding into it. For node 5, what would that look like? You guessed it, the amount of product that's flowing from node 2 to node 5 plus the amount of product that's flowing from node 3 to node 5 has got to sum up to 10 units of material. So that's what the customer consumption constraint looks like. If I look at some of the other constraints, we have the plant capacity constraint. This is saying that the inflow of product going into the plant has got to be less than or equal to the plant capacity. Well, that's also, you could also say that the outflow of material has got to be less than or equal to the plant capacity. But I actually have another constraint in here that says the inflow has got to be equal to the outflow. So it really doesn't matter whether I look at the raw material side or the warehouse side. It would be the same. And the easiest one to do would be the raw materials. So the first equation, the amount that's flowing from node 1 to node 2, node 1 to node 2, has got to be, in this case, less than or equal to 12 if 12 is the plant capacity. And if the plant capacity is 15 for node 3, then the amount flowing into node 3 has got to be less than or equal to 15. So those are the constraints that I would need to set up to model the plant capacity in the mixed integer programming model. The other constraint will be a conservation of flow constraint, as I just mentioned. Here, this is where we're looking at the inflow of product must be equal to the outflow. So for node 2, the amount of product going into node 2 has also got to flow out of node 2. So the amount going from node 1 to 2 here, node 1 to 2, from the raw materials to the plant number 2, has got to equal what's flowing from node 2 to 4 plus 2 to 5. The node going in, the amount coming in has to be equal to the amount going out. And alternatively, if we look at node 3, what goes into node 3 must go out of node 3 as well. So how are we doing so far, guys? Does those equations make sense? Any questions on the constraints so far? Those are the easy ones.
No questions on that so far, Robin. There are two questions here, and I think you're getting to one of these, but I'll bring it up anyways. Someone's asking if you would walk through the LP part of ExtendSim, what block you're using to enter the constraints and the functions and that sort of thing. And then the other question is, what if the cost function was a nonlinear function of the decision variables?
If it was a nonlinear function, you could break it up into piecewise and make it linear and solve it with the LP solve. But LP solve does not do nonlinear functions. You'd have to then go and use some other solver and use the DLL for that, which you would use the DLL of the other solver just like you would with the way you would with the LP solve. But if you was using the LP solve, you'd have to break it up into piecewise linear components. Okay, so yes, I will be getting to the functions that I'm using in just a second here. So the last constraint I want to look at is a single source constraint. And this is what makes it a mixed integer model. What we've looked at so far is just a plain LP model, but because I have the constraint that a warehouse can only look at the material from one upstream plant, as in if for product 3, for example, it can only come from either plant 2 or plant 3. It can't come from both plant 2 and plant 3. And so I have to put up the binary variables in here. And here's what the equation for that would look like. The first one would be, I'm trying to set up the binary variable going from 2 to 4. It would be 0 if no material goes from 2 to 4. It would be 1 if material did flow from 2 to 4. And so this is a constraint that I would look at. If the amount that's going from 2 to 4 is greater than 0, what would the binary variable be? Well, for example, if the amount of products was 10, then the equation would say 10 must be less than or equal to a large number times that binary variable. Well, would it be 0 or 1? Well, if it was 0, that would be not a true statement. 0 is not greater than 10, so it would have to be 1. That would make the statement 10 is less than or equal to the large number true. So if we did have product flowing from 2 to 4, that would force the binary variable to be 1. And that leads us to the next constraint, that only one of those nodes can supply the warehouse. It either has to come from plant 2 or plant 3. So I have the last constraint that I'll look at is a binary variable from 2 to 4 plus from 3 to 4. The node supplying 4 has got to be less or equal to 1. So that would force it to only come from one node. So here's how I did it. With my problem, I was able to bring out, I took my problem and created 3 database tables from that problem. One to look at the objective function, one to model the right-hand side, one to model the constraints. And then I had a 4th table in there to capture the results from the LP solver. Here's what my, well, let me jump out of this, show you what my tables look like. If I go into my optimization controls, I have one table that is dealing with the objective function. And the way I defined it was I have a list of the variable names. And as you saw earlier, some of them is BV variables for the binary variables. You'll see some of the variables with the X. That's the amount that is shipped from one node to another. I'm also listing the coefficient in here, the lower bound, and the upper bound. Now, I'll put a -1 in here in the upper bound if it does not have a negative, if it does not have an upper bound. But they all have a lower bound of 0. And then I listed the variable type, whether it was binary, real, or integer. So that's the first table I set up. Now, when I go into my problem, and maybe if I wanted to only look at a subset, let's take out some of the products and only look at product 1. So I'll only look at product 1. When I build these tables, it will restructure this and only put in the data for product 1. So if you look at, with all 3 products, I had 117 variables, but when I rebuild them with only 1 product, you'll notice now this table only contains 39 variables. So this table is getting rebuilt every time I change the database. So let me put those other 2 products in there and rebuild it. So that's the way each of those tables are working. I'm rebuilding this based on the database tables. For the objective function, the cost, this is where I'm looking at the cost and the distance between 2 nodes. So if you look going from node 2 to node 5 here, that's the variable name. The cost for that is $100 per pallet. Going from node 2 to node 6, that's $20 per pallet. So I'm rebuilding this table based on my cost structure, based on the cost structure that I already talked about here. Another table is a constraints table, where I put into a normalized table where I'm listing the constraint name, I'm listing the variable names, and the coefficient for that constraint. So if I look at a particular constraint, this would be the conservation constraint, at node 2 for product 1. It contains these variables. So if you look at the A matrix, what is required is the column, which is a variable name, and the row, which is a constraint name. So that's how I'm defining the A matrix here. Another table that I'm defining is the right-hand side. This is where I define the constraint name, the right-hand side value, and the equality. I think 1 is less than or equal to, 2 is greater than or equal to, and 3 is equal to. So the conservation constraints is equal to constraints. And I think also some of my binary variables are equal to constraints. So that's what I need to set up in that table. Then when I optimize it, and I have a block here that does the optimization, that's where I'm setting up the optimization table, so I'd optimize it and look at the results. If I look at it, let me go back to the PowerPoint and show you the functions that it's using.
So Robin,
Robin,
this optimizer block is one you've built, correct?
This is one that I built.
Okay.
Now this optimization block does not really focus on the LP solve. Most of the code in the block is getting the model set up into the format that I've just shown. And I have an include file actually there's an include file that ExtendSim puts into the extensions includes folder called lpsolve version 8.h. It's called lpsolve version 8.h. That has all the functions you need to run the lpsolve in it. One of them is to set up the objective function, set up the rows, set up constraint types, and set up the right-hand side. So for example, setting up the objective function, we tell it the problem that we're working with. That's a pointer to the DLL. And then we pass it an array, the row array. So if you recall, the objective function was a column of data that had the variable name in it and its objective function coefficient. So that row array here in the middle tells us what the coefficient is for all of your decision variables. There's another function, set row EX, sets up the constraints. It's trying to set up the constraint, variable, and coefficient. If you recall the second table that I showed you, the constraints, that second function is going to set up the constraint, variable name, and coefficient and pass it into the lpsolve. But that one is one that you have to do one function at a time, one constraint at a time. Then you would pass in the constraint type, and that's basically telling it whether it's less than, greater than, or equal to. And there is another function, the last function that I used was looking at the right-hand side, and that was in a vector form. So all the right-hand side values you'd put in an array and feed it into lpsolve. Let me open up another model. So this block here is basically just taking my supply chain model and getting it set up to feed the data in that format. That the function the header file that the lpsolve could use. Let me open up another model for you though. One of these blocks that Cecile sent, for imagine that, for me to look at, is this, she sent me an LP called the lpsolve block, in which it does the same thing my block is doing, taking your optimization problem and feeding it into the solver. And this is one that we should probably pass out or post on the website, Dave, with the presentation, that would take your decision variables, the objective function, it would take your constraints, the A matrix, and it would take your right-hand side column and push it into the solver. And you can open up the code of it. Oops. since I've had to use about 3 computers getting on here, I might not can find it. But the function called lpsolve version 8.h has all of the code in there to set those functions up. So there wasn't much I had to do on the DLL side. I was basically using the same function that Cecile uses in the discrete rate technology. So she sets all these functions up here, and you could simply call them. Does that make sense, guys?
Robin, I do have one question, but I think maybe we'll leave it to the end because it's we went past the point at which it would have been pertinent, but I don't see any other questions there. So,
okay. Okay. So again, those are the 4 functions that I'm basically using to set my problem up into lpsolve. There are a few other functions that we can talk about later to get it to connect to the DLL and connect up the functions to the DLL. But if anyone's interested, I can talk to you about that in a separate presentation if you're interested in the nuts and bolts of it. This is just here to kind of give you an overview of what's happening here. So first of all, the optimizer is an evolutionary search method. It does have to run multiple iterations, and between each iteration, it introduces the variation to try to find different possible solutions. The value in it is that it tries to not, once it starts finding bad solutions, it doesn't keep going down the path of finding bad solutions. Whereas if you did a full experiment, just a full, if you experimented with every option, you would be experimenting with some bad solutions. And even though we know we would have a bad solution, we'd still be having to experiment with it. But this is trying to eliminate and prune off those bad solutions up front. It is not foolproof, so usually you'd have to run it 2 or 3 times just to make sure that you're not getting local optimums. Let me go through how it works real quick as we're running close to out of time. So first of all, with this optimizer, the problem is stated as having an objective function with either a min value or max value. We have variables that are bounded. We have to give those variables a minimum number and a maximum number. And the constraints would be optional. We would not have to put constraints in there necessarily, but we could. It would randomly set up the initial population. From that initial population of initial guesses, the best members are kept. Then it goes and tries to generate new members with several possible options here of how to generate new members. And it continues until the optimizer thinks that there's probably no better solution out there, as they're all of the solutions are getting about close to each other. Or there's some other terminating conditions. But with each iteration here, it is running the simulation model. Whereas in the mixed integer programming model, it's not. That MIP model is just running a series of well, how would you put it? It's running an optimization, just a mathematical calculation. Whereas with the evolutionary optimizer here in ExtendSim, that is running the simulation at each iteration, and then using that solution to see if it can come up with a better solution. But it has to run the model with each iteration, with each member here. So the most interesting piece of this is how it generates the initial members and of this solution set, and how it generates the new members following up on that. So if I took an example here with variable x, it would have a lower bound of 1. Let's give it an upper bound of 100, just for giggles. This member population, let's set it up to have a size of 4. So the initial population will be set as follows. The first 8 initial members which would be, we'd get those 8 because the population size is 4, and we'd want to do twice the number of the member population. So we'll come up with 8 random scenarios to test. And it will generate that by coming up with the number between the lower bound and the upper bound. Just for giggles, let's say we roll the die and generate those 8 random values for this initial population to test. It's going to run the simulation model with each one of these values and get its objective function. In our model with the supply chain, our parameter that we'd want to test is the what? The safety stock. The bounds would be the lower bound and the upper bound of what we'd expect that safety stock to be. So it would come up with initial population of setting those safety stocks level between its lower bound and upper bound. Then it would solve the simulation model and come up with the objective function. My objective function in the simulation model is to minimize holding costs and to minimize lost cells. So that's what the objective function would represent in my simulation model, to minimize those costs of the holding and the lost cells. And then it would come up with some sort of objective value for that, objective function value for those. In this case, I'm trying to do a maximization of the X parameter between 1 and 100. So I've run the simulation and I come up with a bunch of solutions for this problem. What it would do next is if we look at a number line between 1 and 100 with those 8 solutions, if I'm maximizing, which would be the 4 that I'd want to choose to continue on with? Well, it would be the 4 highest values, right? So I would want to keep in that initial, the member population, the 16, the 8, the 6, and the 8. And the other 4, which has a value of 4, I don't care about those. Those are bad solutions that I don't want to experiment any further with. So I would kick them off the list and just be left with the best 4. That's my member population. That's one of the things that it does to eliminate those bad combinations in our simulation model. It eliminates them and will not test any further on them. Now, so I'm left with the best 4. Now what it does, what it is the way it wants to look at the new members. The way it generates new members is it ranks them. 6 is the worst member now. It will kick it off the list and tries to generate a new member for that, for the 4th one on my population. In generating those new members, it's going to either choose an existing member or choose a number between, for example, well, it's either going to choose a random weighted average between 2 of the members or it's going to choose a new random number. So let's say we do option 2. So it would say, pick, say, 72 and 19, number 1 and number 2, take the some sort of weighted average of them and come up with a value of 45, and then it will want to test value of 45. It will run the simulation and then see what the output will be. So it runs the value of 45 and it gets a value of 10. Great. Now we evaluate it and resort. So that member goes onto the list. Now the next iteration is what? To knock off the next worst one and come up with another member for this, either by choosing an existing member, doing another average, or just choosing another random number. That's what's going on here and how it's trying to do the generation of new members in the optimizer until it terminates. I did set that up in my model, and what I was interested in is the order points. I wanted to see what the proper order point should be for all of the nodes in my supply chain. That would be basically my safety stock as I run it. If I look at my objectives, I set up the order points for all of them. I set the minimum limit and the maximum limit. The DCs, the minimum limit, I said was 100 pallets. The maximum limit, I said was 800. For the, actually those are the plants, my bad. The first 3 are for the plants. The next 6 would be for the DCs, which the DCs don't need as much inventory, so I let them range from 10 to 200. And with the constraints set up to look at lost sales and the holding costs. And I let it optimize that. It took actually about an hour to do that. And I actually have about 27 input parameters in here. And that's, of course, I didn't have to mess with the order points for the raw materials, but all the other 9 locations. You have 9 locations and 3 products, so that's where we get the 27 from. And it took about an hour to solve. And if you look at the way I've labeled the variables, OP would be the order point. 2.1 is the order point for location 2, which is plant, product number 1. This is location 3, product number 1. Location 4, product number 1. Location 5, product number 1, and location 6, product number 1. So if you notice the first 3, order point for location 2, 3, and 4, notice how they are a lot higher than the other order points, which are warehouses. Some of the warehouses do have quite a bit of inventory, but not all of them. Could be the way the network is set up, but that's what you can see with it. And this gives you a good starting point where this wouldn't be the end-all, do-all. You wouldn't want to say, yeah, this is my order point that I want to stick with. What you'd want to do now is say, yeah, this is a good starting point. Now let me go into ExtendSim, set up the scenario manager, and run some iterations around the best combination here to see, well, it might not be exactly 223, but we'd want to run it multiple iterations, say 30 iterations at 233, 30 iterations at maybe 220, 30 iterations at 240, and see what value we'd have at increasing that order point or decreasing it. So the next step is still to go into and do some sensitivity analysis on it. Questions?
Robin, I've got a couple questions here. They go back a ways. Do you want those now or when you're done?
Okay. Now is good.
Okay. So one question is, how do you equate in equals out for a plant when there is storage involved?
So that's dealing with the optimization piece.
Mm-hmm.
And the optimization is not looking at storage. It's dealing with one iteration, one time period, and if the in was more than the out, then it would build up. It would continuously build up. But it's kind of a different situation than what we're looking at with a simulation model. In a simulation model, we are looking at the flow of items as they go in through the system. Well, in the optimization world, we're not doing that. We're looking at just making sure that the input is equal to the output. If we have the input equal, if the input was more than the output, then the plant is going to explode because it's always going to be more. If it's less than if the input is less than the output, then we can't supply it. So it's just a mathematical formulation to make sure that we have enough material to supply it mathematically. We're not looking at variation. We're not looking at any sort of time series in there. We just want to make sure that through each of the periods, we will have enough product to say that if 10 goes in, 10 is going to go out.
Another question is, I'm not sure I understand the MIP setup. How does it account for variability or stochasticity of, say, a cost coefficient?
So if I was to do that, that would Yeah, I'm not considering that at all.
I was thinking you might set that up actually in the ExtendSim model so that each time you evaluated that, you still have to have, that's one thing linear programming doesn't deal particularly well with is randomness.
Right.
But you could, from the simulation model, saying every time I evaluate this, I'm going to have a different cost, and that could be drawn from a random value in the simulation model. I'm not sure if that's what's being asked here, but that would be one way of looking at that.
Yeah, so the way I see it, since I'm doing a simulation model to follow it up with, I would tend to make the LP model or the mixed integer model as simple as possible, and do more of the randomness or the cost functions like you described more in the simulation piece to look at it there.
I mean, one way of thinking about it, and correct me if I'm wrong here, Robin, is to say use the expected cost, because when you're using the LP model to make a decision, and so you're going to make a decision based on the expected cost, and then the simulation model to reflect the actual cost, kind of working with the strengths of both technologies there.
Correct.
Another question is, can the optimizer handle multi-objective function optimization? And is that the ExtendSim optimizer, I think is what is being referred to?
I think the answer is no in most cases. In the DLL with LP solve, I think for that you'd have to use, again, another solver. And for the optimizer, yeah, that's not an option, I don't believe. I've never used.
Yeah, the only thing you could do is weight. You know, you would have to put them into one optimization equation, and you could have multiple components of that are weighted differently. So you could say you want to have not only your minimum cost is not only your lost sales and your holding cost, but maybe you include a component which is the shipping time, where you want to meet a certain criteria of shipping time. I guess that's a constraint. So I'm not thinking of anything, but you could put more factors into your minimum cost function, and that could be quite complex. But you do have to boil it down into one min cost or max profit equation. Here's another question. If I set up the problem wrong and the problem was infeasible, how would I go about debugging, and does LP solve return a duality gap?
I don't think it returns a duality gap. Here's what I used when I was setting it up to help debug it. Let me find. It does output. Let me run it again. When you run it, it does generate some output files, and that shows you basically the LP or the MIP that you put in there. This is what I was using to debug it to make sure my constraints was correct. Where it does show you the formulation, as far as other outputs, I haven't looked at that yet. I'm sure it does, but I have not got into that.
I don't see any additional questions, Robin.
Okay, well, if anyone is interested and would like to see a little bit more of the nuts and bolts of it, I would be happy to follow up with another session on separate from this, on either on the supply chain model that I did, or the optimization with the LP solver, the nuts and bolts of it, or the evolutionary optimizer, how to set it up. And the other session will be more about how to set it up to get it to work than about the overall gist of how it works in this case. If anyone would be interested, just send me an email and let me know, and we could do that offline sometime.
And actually, if there's a group of people, we can set up another session, either inside of or outside of the masterclass series. Oh, and I've got a couple of comments here that we'd be happy to host that, so we could set up a time and use the same mechanism, which seems to work pretty well. Actually, Cecile, who originally developed the interface to the LP solver here at Imagine That, has said LP Solve has an executable which provides more information. So there is more information on debugging it, and there's an online group of people that work with LP Solve, so there's quite a bit of information about working with that. And we do have one person here that's interested in a follow-up session. So maybe we'll set up another group, another webinar with a follow-up, if that works for you, Robin.
Works for me.
Okay. Yeah, we have a couple people here interested. So, well, thank you very much, Robin. Did you have anything else that you wanted to add?
Nope, I'm good. I just appreciate everybody for attending, and I hope I answered some of your questions that you might have had. Hope it was valuable for you.
Well, yeah, thank you. This is a lot of material to cover in an hour. You've really covered 3 different technologies: simulation, linear programming, or integer programming, and the ExtendSim's optimizer, which is evolutionary optimizer. So that's a lot to try to cover in 1 hour. But that's
one of the things that I was wanting to get across in this is that, you know, one tool can't solve everything for you. So each of these different technologies brings another piece of, can answer a different piece of the question that the others might have a difficulty in answering. It's just that when you solve them with different tools outside of, you know, with different applications, it's tough to interact with it. However, if you do it all in one application like this and use the ExtendSim database as a back end to it, it makes it fairly seamlessly. It integrates fairly seamlessly.
Yeah, that's an excellent point. We're seeing more and more people combine different operations research technologies together, and that's absolutely right. If you've got a problem, the most sophisticated operations research analyst will choose from one of or more tools in a toolbox, rather than just running around and applying simulation or optimization or decision theory to every single problem they run into. What you want to do is pick the appropriate tool, and in some cases a combination of tools like you've done here. So that's an excellent example. Well, thank you very much, Robin. I think you've done a great job in presenting a lot of information in a relatively short time period. Don't forget that the next session will be in September on Bayesian theory and simulation together, and then following that in October with Dr. Ava Law on design of experiments. Both should be very good sessions, and we look forward to seeing them. I don't see any more questions here, so Robin, I think if we're done, we'll end the webinar. Thanks again.
Thanks, Dave.